Hi everybody, we are going to start talking about the mean value theorem, which is another application of derivatives. So in math, when we say the word mean, we are talking about the average. The mean value theorem compares the average rate of change with the instantaneous rate of change. All right, we have already talked about average rate of change, and we know that that really just means regular old slope. We've also talked about instantaneous rate of change, and we know that that is the slope of the tangent line, which is the derivative. All right, so we're going to talk about what this theorem actually says and when we use it before we dive into some examples. So the conditions really just mean like, hey, if these are met, then we get to talk about this theorem. So the conditions are really the ifs of the theorem. So if f of x is continuous on the interval a to b, with the endpoints included, so notice these are brackets. That means that the endpoints are included. All right, then that means we can't have open circles on the end, really. That's all that means, that they have to be closed circles on the interval we're looking at. So that's the first condition. The second condition is that it must be differentiable on the interval a to b, but this time a and b do not have to be included. The endpoints are not included. All right, so these are our two conditions, that f of x must be continuous and differentiable. The conclusions then, so the thens of our theorem, the mean value theorem says if these two conditions are met, then the instantaneous rate of change, so the derivative, at some value c, all right, which has to be a number between a and b, the average rate of change at some point c must equal the instantaneous rate of change on the interval. No, the average rate of change on the interval, I'm sorry. The instantaneous rate of change at point C must equal the average rate of change over the interval. And we know that average rate of change is just the slope. So f of b minus f of a over b minus a. That's our regular old average rate of change, our slope. So I know it sounds a little funny, and I promise once we talk a little bit more about what it's used for and look at some examples, it's actually not that bad. Okay, we have to get the instantaneous rate of change at some point to be equal to the average rate of change at some point. That's what the mean value theorem tells us. If these conditions are met, then this has to happen. So we use the mean value theorem when we're trying to guarantee that a function has a specific slope value, we also use it when we're trying to locate the place where a function's average rate of change is the same as its instantaneous rate of change. So we've got two kind of problems here. So let's look at the first one. F of x is defined by f of x equals 1 minus x cubed. What are all the values in c, the values of c, excuse me, in the closed interval 0 to 3 that satisfy the conditions of the mean value theorem? Well, in order to apply the mean value theorem, we have to first make sure that the conditions are met. So the first condition is that f of x must be continuous. Well, when we think about this function here, this is a cubic function, which is a polynomial, and we know that a cubic function looks like that, which is continuous everywhere. So I usually put like a little check mark then, like, hey, yep, I checked that it's continuous, we're good. The second condition is that f of x must be differentiable. Well, again, we know what this graph looks like. We've seen it a bunch. So we know that there's no corners, there's no cusps, there's no asymptotes, no other forms of discontinuity. All right, so we know that f of x is differentiable on the interval. So again, I put a little check mark. So since both of these conditions are met, we can apply the mean value theorem, which says that the instantaneous rate of change must equal the average rate of change at some point on the interval. So we know that 0 must be our A and B must be our 3. So what I like to do is I usually go over to the side and I find my f of 0 and my f of 3, because I like to do it on its own so I don't mess up with negatives or anything. So if I plug in 0, I get 1. And if I plug in 3, I get negative 8. So we need to talk about what this f prime of c means. That means that we need to take the derivative of our function, and it's at some c value. So what I'm going to do is I am going to take the derivative, and I'm going to plug in c. So if I take the derivative of this function here, I'm going to drop the 3, and I get 1 minus x raised to the second, and then I'm going to multiply by negative 1. And I know if I simplify that, I get negative 3, 1 minus x squared. And this is my f prime of x. Well, if I want to do f prime of c, that means it's just negative 3 times 1 minus c squared. And now I have all of the pieces that I need in order to plug into my formula here for mean value theorem. So I'm going to get negative 3 times 1 minus c squared. That's my f prime of c. And that has to equal my average rate of change over the interval. So f of b would be negative 8 minus f of a, which is 1, over 3 minus 0. That means I get negative 3 times 1 minus c squared has to equal negative 8 minus 1 is negative 9 over 3, which is negative 3. So right now I have my instantaneous rate of change at c, and it has to equal my average rate of change, which I got to be negative 3. Now I just have to solve for c. So I can divide both sides by negative 3, get 1 minus c squared equals 1. If I take the square root of both sides, I get 1 minus c equals plus or minus 1. And then I always write them separately. So I get 1 minus c equals positive 1, and 1 minus c equals negative 1. So I know this is going to give me c equals 0, and this is going to give me c equals positive 2. All right, those are my two values of c. We always have to go back and check to make sure that these are both in the interval. So we're looking at the interval from 0 to 3, and we got c equals 0 and c equals 2. Both of those fall in the interval, so we know that we're good. If one of these fell outside of it, we would call it an extraneous solution, and we would just say it falls outside the given interval. Okay? Let's take a look at another type of example that we have. So applying the mean value theorem to this function g of x guarantees that there exists some value c between 0 and 2 such that g prime of c equals, and we're trying to find that specific number. So this one is a little different. This one is actually, instead of asking us to find c like it did in number 1, it's really just asking, what does the slope have to be? What is my instantaneous rate of change at this value c? It's not even asking us to find c. So we know that the instantaneous rate of change has to equal the average rate of change. So it has to equal g of 2 minus g of 0 all over 2 minus 0. So again, I usually like to go over to a different spot to actually do my g of 2 and my g of 0, just so I don't mess up my negatives and stuff. So g of 2, if I plug 2 into here, 2 squared is 4 times 3 is 12, plus 2 times 2, which is 4, plus 1. So my g of 2 is actually 17. G of 0 means 0, 0, so I get a 1. Alright, so that means that g prime of c has to equal 17 minus 1 over 2. And if I simplify that down, I get that it has to equal 8. So just like this one, where I simplified it down and I got that my average rate of change was -3, that's what my instantaneous rate of change had to equal. In this one, I actually solved for c to figure out when does that happen. In this one, it's actually just asking for that slope. So our answer is 8, which is choice B. Question 3 says, how many of these functions do not satisfy the mean value theorem? Well, we know that the mean value theorem, the conditions are that it has to be continuous on the closed interval a to b, and it has to be differentiable on the open interval a to b. So this is asking how many of them do not satisfy the mean value theorem. So what I would do is I look at each one and I decide, does it break one of these conditions? All right, so this first one right here, if we look at it, we can clearly see that that's an open circle at A, and that it's filled in up there, but that's an open circle, it's a removable discontinuity, which means it's not continuous on the interval. So that means this one is going to be a problem. For the second one, it's continuous everywhere, which is great, but the problem here is that I can see it's not differentiable everywhere. There's either a cusp or a corner going on there. Kind of looks like a cusp to me. But either way, it's not differentiable on the interval, which means that is also a problem. The third one, that's a nice smooth curve, which is continuous, and it looks like it gets kind of vertical, but there's not actually a vertical tangent there. If we were to draw in those tangent lines, none of them would be completely vertical. So we would be okay. This one is actually all good. The fourth one, we can see that it's definitely not continuous because there's a vertical asymptote right here. So that is also one that does not satisfy the conditions. So altogether we have 3 in total. For question 4, we're given a function that is continuous, and f of -2 is equal to f of 2, which is equal to 0. If there is no value of c where -2 is less than 2, if there's no value of c between -2 and 2, for which f prime of c equals 0, which of the following statements must be true? Well, when we think about the mean value theorem, we know that f prime of c has to equal the average rate of change. So f of 2 minus f of negative 2 all over 2 minus negative 2. And we know that f of 2 is 0, f of negative 2 is 0, which means that f prime of c equals 0 if we were able to apply the mean value theorem. And we're not able to do that because it says that there is no value of c where f prime of c equals 0. That means then that the mean value theorem cannot be applied for some reason, which means one of the conditions must not have been met. So what we need to do is figure out which of these statements must be true then. So when we look at choice A, it's saying that between negative 2 and 2, f prime of k is greater than 0. Well, I don't really care if it's positive or negative. That doesn't really matter to me at all. So that's definitely not an option. Choice B is actually the same as choice A, which means that's definitely not the correct answer for us. Part C says that between negative 2 and 2, f prime of k exists. It means that the derivative exists everywhere. But it doesn't matter if it exists everywhere. What we're looking for is one of the conditions of mean value theorem to not be met. Question D says that between negative 2 and 2, f prime of k exists, but f prime is not continuous. That's not a condition for mean value theorem either. Part E, though, says for some k between negative 2 and 2, f prime of k does not exist. This must be the part that is true. If we go back to part C for a second, f prime of k exists means that it's differentiable on that interval. If it's differentiable on that interval, then MVT should be applied. But since this says that MVT cannot be applied, this must not be true. We have to keep in mind that we're looking for one that must be true here. So it has to be choice E, saying that f prime of k does not exist at some point. Okay? We're going to do question 5 together in class, just to make sure that we are all good, and we will do some practice. I'll see you guys later.